So, how do we actually listen to our planet? I'm not talking about the oceans or the weather. I mean the deep, silent movements happening miles and miles right under our feet. In this explainer, we're going to dive into the incredible tech that lets us hear the Earth's heartbeat, from the absolute faintest tremor to the most powerful city toppling quake. Right. This is the fundamental challenge for seismologists, and it's an engineering problem on a scale that's kind of hard to wrap your head around. The ground can move by less than a nanometer, that's smaller than an atom, but it can also shift by several meters. Being able to capture both of those extremes, that takes an instrument with almost unbelievable sensitivity and toughness. The key to solving this whole problem is a concept called dynamic range. Think about your own hearing. You can hear a pin drop in a quiet room, but a jet engine right next to you would be, well, painfully loud. The range between that quietest pin drop and that loudest jet engine, that's your ear's dynamic range. For a seismometer, that range has to be way, way wider. And here's the number that puts it into perspective. The best modern sensors can hit a dynamic range of over 150 decibels. That's just incredible. And what's really cool is that our digital technology is perfectly matched to handle it. A 24-bit digital recorder is the ideal partner, making sure we capture everything from the faintest whispers to the loudest roars without losing any detail. Okay, so where does the journey of an earthquake signal even begin? Well, it all starts with the sensor itself. This is an instrument designed to do one single thing: turn the physical shaking of the ground into a clean, measurable electrical message. The physics behind this is actually pretty elegant. It all comes down to one simple principle: inertia. An object at rest wants to stay at rest. So when the ground suddenly shakes, a heavy mass that's suspended inside the seismometer tries to stay perfectly still. The instrument's frame moves with the Earth, but that weight kind of lags behind. And that's the key. By measuring that tiny bit of relative motion between the moving frame and the still weight, we can figure out exactly how the ground moved and turn that into a voltage. Of course, we've come a long, long way from just a simple pendulum. I mean, take a look at this. This is a modern, high-tech borehole seismometer. It's specifically built to be lowered deep down into the Earth. Now, why would we go to all that trouble? Because down there, it's quiet. It's totally isolated from all the surface noise, traffic, wind, you name it. This lets it hear the planet's true vibrations with stunning clarity. And that quiet is so important because it brings us to the next huge challenge. That tiny electrical signal coming from the sensor is incredibly vulnerable. It's like trying to hear a single whisper during a hurricane of background noise, coming from both the environment and from the electronics themselves. This chart shows the problem perfectly. It's what we call the noise floor. Think of it as the constant baseline hum of our planet and our electronics. It's caused by everything from the random jiggling of atoms, that's thermal noise, to the tiny bit of noise inside any electronic part. For an earthquake to even show up on our radar, its signal has to be strong enough to pop its head up clearly above all that background chatter. The first line of defense against this noise isn't electronic. It's geologic. It's all about location, location, location. If you build a station on soft, loose sediments, it's going to pick up a ton of local noise, and faint signals will just get lost. But if you anchor a station directly to solid bedrock, now you've got a much lower noise floor and a crystal clear window into what the Earth is doing. All right, so once we have that clean, analog signal, the journey enters the digital world. We've got to convert that smooth, continuous electrical wave into a series of numbers, data that a computer can actually store, send, and analyze. The hero of this part of the story is the analog to digital converter, or ADC. Its job is to take super fast snapshots, or samples, of that analog voltage, we're talking thousands of times a second, and assign a precise number to each and every one. This stream of numbers becomes the raw data of modern seismology. But here's the catch. You have to sample fast enough. If you don't, you get this really bizarre effect called aliasing. It's just like when you watch a video of a car and the wheels look like they're spinning backward. The camera's frame rate is just too slow to capture the real motion. The exact same thing happens here. If you sample a seismic wave too slowly, you don't just miss some info, you actually create a totally fake, distorted wave in your data. That's why the golden rule is you have to sample at least twice as fast as the highest frequency you're trying to record. So, this leads to a huge practical problem. A single seismic station is just pumping out this relentless 24/7 stream of data. And most of it, it's just background noise. How on earth does a computer sift through this ocean of numbers to automatically flag the exact moment an earthquake begins?
The solution is a simple but totally brilliant algorithm called STA/LTA. Let's just walk through this graph here. The computer is constantly calculating two things. First, there's the long-term average, or LTA. That's the pretty flat line that represents the normal background noise. Second, you've got the short-term average, or STA. See how it follows the signal much more closely? Now, when an earthquake hits, the signal's amplitude shoots up. You can see that STA line just spike in response, while the LTA kind of stays behind. The moment the ratio between those two, that's the bottom line, crosses a set trigger level, bam, the system declares an event. We've got an earthquake.
But detecting a quake at just one station is really only the beginning. To truly understand it, to know exactly where it happened and how big it was, we need more than one listener. We need a whole network to connect the dots and build a global picture. And the magic number for this is 3. Yup, 3. With arrival time data from at least 3 different stations, seismologists can use some pretty simple geometry to triangulate the earthquake's origin, its epicenter. Think about it. One station tells you how far away it was, but not which direction. 2 stations narrow it down to 2 possible points, but that third station, that nails the exact location. And that basic need is what gives rise to these absolutely massive networks. You have hundreds of individual stations, a lot of them in really remote places, all linked up to form regional networks. Then, those regional networks are combined, sharing data in real time, to create a global web of thousands of seismic sensors all listening together. But this creates a monumental new problem. For that triangulation to work, every single station in that global network has to have a perfectly synchronized clock. And as this quote from our source material points out, for decades, getting that timing right was an absolute nightmare, a total headache that caused endless frustration for scientists. So what was the solution? Well, it didn't come from seismology. It came from space. GPS, the very same system that helps you navigate in your car, provides an incredibly precise time signal, down to the microsecond, to any receiver on the planet. By putting a cheap GPS receiver on every seismic station, the timing problem was solved, basically overnight. And that's what made truly global, real-time seismology possible. So, after this whole journey, from a faint vibration in the rock, through a sensor converted to digital data, flagged by an algorithm, and then shared across a network that's synchronized by satellites, what's the payoff? What do we actually learn from listening so closely?
Well, the payoff is a fundamentally new way of seeing our own world. We can pinpoint earthquake locations in minutes, which is absolutely crucial for emergency response. By studying how seismic waves travel through the planet, we can basically give the Earth a CAT scan, mapping out the mantle and the core. We can even detect the subtle tremors of magma moving deep under volcanoes, giving us vital warnings before they erupt. It's basically a continuous health check on the powerful forces that are always shaping our world.
This vast global nervous system that we've built is always on, always listening. It's really a testament to human ingenuity, a brand new sense that lets us perceive our planet in a way our ancestors could never have imagined. We've learned how to hear the Earth's heartbeat. So the only question left is, what's it going to tell us next?